Ladies and gentlemen, welcome to the Shaw Prize Lecture in Mathematical Sciences 2023, hosted by Shaw College of the Chinese University of Hong Kong. May I first invite Professor Freedom Leung, head of Shaw College, to deliver his welcoming address. Professor Leung, please.
Professor Drinfeld, Professor Yao, Professor Yang, distinguished guests, colleagues, students, ladies and gentlemen, good evening. Welcome to Shaw College, and welcome to the Shaw Prize Lecture in Mathematical Science 2023. For the past 3 years, the Shaw Prize Lecture could only be held virtually due to the COVID pandemic. So, we are much delighted to see you and our Shaw Laureate here this year, in person actually. The Shaw Prize was established in 2002 under the auspices of Sir Run Shaw to honor individuals who have made outstanding contribution in academic and scientific research discoveries. Since the first Shaw Prize presented in 2004, Shaw College has been very honored to be chosen to host the Shaw Prize Lecture every year on one of the 3 prizes: astronomy, life science and medicine, or mathematical science. This year is our turn to host Shaw Prize Lecture on mathematical science. I would like to congratulate Professor Vladimir Drinfeld and Professor Shing-Tung, who is also our college honorary fellows, for their achievement in mathematical sciences. We are very honored to have Professor Drinfeld and Professor Yao here today to share their discovery in mathematical science with us. We are also grateful to Professor Kwok-Wai Chan from the Department of Mathematics to introduce the Shaw Laureates and moderate a Q&A session later on. Last but not least, I also want to welcome all our CHK Shenzhen colleagues and students coming all the way from our Shenzhen campus to attend this lecture. Now, may I pass the time back to our MC.
Thank you, Professor Leung. May I now invite Professor Kwok-Wai Chan from the Department of Mathematics of CHK to introduce the Shaw Laureates in Mathematical Sciences 2023. Professor Chan, please.
Good afternoon, ladies and gentlemen. This year's Shaw Prize in Mathematical Sciences is awarded in equal shares to Professor Vladimir Drinfeld and Professor Shing-Tung for their contributions in mathematical physics, arithmetic geometry, differential geometry, and scalar geometry. Professor Vladimir Drinfeld is currently Harry Pratt Jusen Distinguished Service Professor of Mathematics at the University of Chicago, USA. He received his bachelor's degree and PhD from Moscow State University, USSR in 1974 and 1978, respectively. He then assumed teaching positions in universities in USSR and served as a research fellow at B. Werkin Institute for Low Temperature Physics and Engineering in Ukraine from 1981 to 1998. He has been professor of mathematics at the University of Chicago since 1998. Professor Drinfeld was honored to the Fields Medal in 1990 and the Wolf Prize in 2018. He is a member of the U.S. National Academy of Sciences and the American Academy of Arts and Sciences, and at the same time, a fellow of the Academy of Sciences, Ukraine. The Mathematical Sciences Selection Committee of the Shaw Prize Foundation acclaims Professor Drinfeld's work, including the invention of Stukas and launching of the geometric Lang-Length program as a pillar of arithmetic geometry, which is at the core of new developments in the field. Professor Shing-Tung is currently Chair Professor and Director of Yao Mathematical Sciences Center at Tsinghua University, PRC. He studied at the Chinese University of Hong Kong from 1966 to 1969 and received a PhD in 1971 from the University of California, Berkeley, USA. He started his career at the Institute for Advanced Study at Princeton University and taught at a number of universities in USA before finally joining and settled in Harvard University since 1987, where he has been a distinguished professor of mathematics and professor of physics. And he has been the director of the Institute of Mathematical Sciences at CHK since 1993, and also a distinguished professor at large since 2003. Professor Yao has won numerous international awards in both mathematics and physics, including the Fields Medal in 1982 and the Wolf Prize in 2010. He is also a member of the Chinese Academy of Sciences, the US National Academy of Sciences, and the American Academy of Arts and Sciences. The Mathematical Sciences Selection Committee of the Shaw Prize Foundation regards Professor Yao's work as having a deep and lasting impact on both mathematics and theoretical physics. His systematic use of PDE methods in geometry and physics, which is now turned into a subject called geometry analysis, allows him to give proofs of the Calabi conjecture and also the positive mass conjecture and the black hole existence theorem. So we shall start today's lectures with Professor Drinfeld. His lecture title will be Toward Shimurian Analogues of Barsotti-Tate Groups. Let's welcome Professor Drinfeld.
I'd like to thank the organizers for inviting me to give this lecture, and I'd like to thank the audience for coming to it. As the title of my lecture is Toward Shimurian Analogues of Barsotti-Tate Groups. Let me say a few words about the title. The word toward from the title is very important. I will be discussing an emerging theory due to many people, rather than a theory which already exists. Another word from the title is Shimurian. It refers to the notion of Shimura variety. We will discuss it later if we have time. Now, let me say a few words about the setting and the notation. Once and for all, we fix a prime p and a positive integer n. The letter capital R will usually denote a commutative ring, and by default, all rings will be assumed commutative. We will be especially interested in the rings R such that P is nilpotent in it. For instance, we are interested in fields of characteristic P. Now I have to discuss the notion of BTN group over a ring R. This notion is due to Grothendieck. BTN is an abbreviation for the words untruncated Barsotti-Tate. Before giving the definition of a BTN group, let me explain the format of the definition. The format is as follows. A BTN group over a ring R is a commutative finite group scheme G over R killed by b to the n, and this group will have to satisfy certain extra properties to be formulated later. Let me first formulate the extra properties in a very simple situation. The simple situation is as follows. Let R be an algebraically closed field of characteristic 0. In this situation, a finite group scheme is the same as a finite abstract group G. In this situation, there is only one extra property, and a very simple one. Namely, G should be flat as a module over the ring Z mod p to the n. For this ring, flat is the same as free. And so our group G should be isomorphic to Z mod p to the n raised to the power of h, where h is a number, and this number h is called the height of G. Now, what is the order of such a group G? So the order of Z mod p to the n is, of course, p to the n. So the order of G equals p to the n h. Equivalently, we can express h, the height h, in terms of the order of the group as follows. The height equals the logarithm of the order with base p divided by n. So here everything is simple. Now let us proceed to the definition of BTN group over ring R. I will give the precise definition only under the following assumptions. First, I will assume that is a field, and I will also assume that the number n is strictly greater than 1. Without these assumptions, the definition is slightly more complicated. If you are interested, you can find it in the expanded version of my talks. So most probably the slides of this talk are posted somewhere online. But in addition to the slides, there is an expanded version, which probably the Shaw Foundation posted it somewhere online. But independently of this, I posted it in the standard ePrint archive, and this is my last ePrint. So if you want to find more details and without, so to say, time restrictions, then you could look at this preprint and at other articles I referred to in the ePrint. Okay, so let me proceed to the definition of the BTN group, assuming that R is a field and n is greater than 1. First of all, recall that a BTN group is not really a group, but a group scheme over. And in other words, it's a group object in the category of schemes over R. Now, we are considering the case when R is a field. In this case, commutative finite group schemes over a field form an abelian category. Now, under our assumptions, namely if n is greater than 1 and R is a field, then the definition is as follows. A BTN group is a flat Z mod B to the n module inside the abelian category of commutative finite group schemes over R. There is a notion of order of a BTN group and the notion of height. The order is defined for any finite group scheme. If you have a finite group scheme, G, let's say over a field, then you look at its coordinate ring. This coordinate ring is a vector space over your field, and because the group scheme is assumed to be finite, this vector space is finite dimensional, and its dimension is called the order of G. And the height of now, if G is a BTN group, then its height is defined by the formula which we already encountered in the previous slide, namely the height h is the logarithm of the order of the group divided by n, logarithm with base p. From this definition, it's not quite clear that the height is an integer, but it is. Please believe. Please believe. Now, let me give an easy example of a BTN group. First, an easy example, and then an interesting example. Let R be a ring. Consider the group scheme over R formed by p to the nth roots of unity. This group scheme is denoted by mu p to the n. In other words, mu p to the power of n is the kernel of the endomorphism of the multiplicative group given by raising to the power of p to the n. Now, it's not hard to see from this that mu e to the n is a BTN group whose order equals p to the n, and therefore its height equals 1. Now let us look more attentively at the case where R is a field of characteristic P. As I said, the order of mu p to the power of n equals p to the power of n. However, I claim that if you if you look at the points of the group in the naive sense, then it has only a single point, which is of course the unit. Indeed, let us check this. We are interested in the roots of the polynomial x to the power of p to the n. So what does it mean to be p to the nth root of unity? This means that x to the power of p to the n should equal to 1. Now, the remarkable feature of characteristic P is that in characteristic P, the polynomial x to the power of p to the n minus 1 equals the p to the power of nth power of x minus 1. And this is easy to see if you apply the binomial theorem and notice that all intermediate binomial coefficients are divisible by p. And because of this remarkable identity, we see that our polynomial has a single root in the naive sense. However, this root occurs with multiplicity p to the n, and if you wish, this is the reason why the order of the group scheme is p to the power of n. This was an easy example, not a very interesting one. Let us now consider an interesting example or class of examples of BTN groups. And in some sense, these examples are typical, so I will discuss typical BTN groups. Let A be an abelian scheme over our ring R. Another way to say it is that A is a family of abelian varieties parametrized by the spectrum of R. Now consider the endomorphism of A given by multiplication by p to the n. And consider the kernel of this endomorphism. Let us denote it by G. It is known that in this case, G is a BTN group, and moreover, its height equals 2D, where D is the dimension of A. More precisely, D is the dimension of A relative to the base spec R. Let me explain why the number 2D occurs here. To see this, let us consider the case where R is the field of complex numbers. In this case, we know that an abelian variety is a complex torus of complex dimension D. In this case, the real dimension of the torus is 2D, and therefore the kernel of multiplication by p to the n in this real torus of dimension 2D is a free model over z mod p to the n, whose rank equals 2D. And this is why 2D occurs here. But now let us look what happens if R is an algebraically closed field of characteristic P. For instance, you can assume that R is the algebraic closure of Fp. This case is much more interesting, and the interesting thing is that in this case the structure of G depends on the abelian variety A. And this is in fact very good. In some sense, this is why the kernel of multiplication by p to the n in A is worth studying. It tells us something about the abelian variety or itself, or in a more general situation, it tells you something about the abelian scheme itself. As I said, the structure of G depends on the abelian variety. Let me say something more precise. If the abelian variety has dimension 1, one-dimensional abelian varieties are called elliptic curves. In this case, as I said before, the height of G equals 2D, and in our situation, the height equals 2. Now, it is known that for all but finitely many elliptic curves over Fp bar, the group G is isomorphic to the direct sum of Z mod B to the N and the group mu B to the power of N. However, there exist exceptional elliptic curves for which this is not true. The exceptional elliptic curves are called supersingular. If A is, it is known that if A is supersingular, then the group of naive points of G is 0. However, the group scheme G itself is quite interesting, and it's, well, I would prefer not to describe its structure in this lecture. There is simply no time for this. But just please believe me that it's understandable and interesting. Let me now discuss the stack of BTN groups. Given a ring R, so let us fix a number h, the height. And given a ring R, let us introduce the notation BTNH of R. This is the notation for the groupoid whose objects are all BTN groups of height h over R, and whose morphisms are isomorphisms of BTN groups. So for each ring R, we have this groupoid BTNH of R. So we get a functor from the category of rings to the category of groupoids. Now, here is my next claim. The claim is that this functor is an algebraic stack of finite type over Z. Now, please believe me that this is very easy. Of course, for most of you, the subject is not very familiar, but once you understand the definition, and if you are relaxed enough, then you see that it's obvious. But now, what is the meaning of the word algebraic stack of finite type? This means that BTNH can be represented as a quotient x modulo gamma, where x is a scheme of finite type over Z, and gamma is a smooth groupoid acting on X. Here, the word quotient is understood in the sense of stacks. It's a quotient stack. So, as I said, the statement is easy. It's proved by very straightforwardly unraveling the definition of BTN groups. Now, this straightforward proof yields a concrete presentation of the stack BTNH as a quotient x mod gamma, but a key fact of life is that this presentation is not illuminating at all. It conceals almost all interesting features. In particular, the scheme X in this presentation is defined by a system of equations for a huge number of unknowns, and the number of equations is much bigger than the number of unknowns. So it's a bad symptom. Let me now formulate the problem I will be discussing. In addition to the number n, let us fix another positive integer m. And let us consider the reduction modulo b to the m of the stack btnh. This reduction will be denoted by bt and mh. In addition to h, we have two positive integers, m and n, which I would consider as truncation parameters. So the integer n is the same as in btn, and the integer m is related to p to the m. So we are studying the reduction modulo b to the m. So btnmh is a stack over the ring of integers modulo p to the m, m as in Mary. Now, here is a problem. Find a nice description of the stack btnmh for any h and n. Now, the question is, what is the meaning of the word nice? As I already said, if you straightforwardly unravel the definition, then you get some description of the stack btnmh. But this description is not illuminating at all. When I say nice description, this first of all means that it should be illuminating. This is a kind of informal criterion. But there is also a more precise criterion for being a nice description. I want the description to be Shimurizable. Please forgive me for introducing this new word. It refers to the notion of Shimura variety. So the Shimurizable means admitting a generalization related to Shimura varieties. If we have time, I will say something about Shimura varieties, but for now, this is just a word. Now, let me say something which is somewhat meaningful, even if you know nothing about Shimura varieties. I want to fill the following table. I hope you see the table. And there is a question mark in this table. And I want to replace the question mark by something. But let us first look at the upper row of the table. And the upper, so what is the upper row? GLH stands for the general linear group of order H. This is an algebraic group, a reductive, more precisely a reductive group. Then in the same upper row, we have the stack BT and MH. Now, I claim that there is a certain relation between BT and MH and the algebraic group GLH. I didn't explain this relation, so please believe me that there is such a relation, and you see this relation from Dieudonné's theory. If you don't know what Dieudonné theory is, then it's okay. Just please believe me that there is some very close relation between the stack BT and MH and the group GLH. But now, in addition to GLH, there are other reductive groups. In particular, there are so-called exceptional groups. For instance, there is an exceptional semi-simple group of type, there is an exceptional reductive group of type E7. Now, I would like to have a stack whose relation to E7 is similar to the relation between the stack BTNMH and the group GLH. Now, you can ask me why E7. As many of you know, there is an even more interesting exceptional reductive group of type E8. Why I am talking about E7 but not E8? The reason is that there exist Shimura varieties of type E7, but there are no Shimura varieties of type E8. And so my hope or conjecture is that whenever you have a Shimura varieties of certain type, you should also have a kind of analog of the stack BTNMH related to this Shimura variety. So I have formulated a problem. Let me say a few words about the status of the problem. Now, there are two aspects of this story. Number one, many people have worked on the problem or on closely related. And the first one to work on this type of problems was Dieudonné, who started to work on this subject many years ago, precisely in the year when I was born, 1954. And Dieudonné's main result was an explicit description of the groupoid of R points. He gave an explicit description of the groupoid BTNMH of R in the case where R is a perfect field of characteristic P. And here the word perfect is very important. His answer involves the group GLH. And this relation to GLH was mentioned on the previous slide. And moreover, a nice feature of his description is that it's Shimurizable. So as I said, many people have worked on the problem. On the other hand, the problem is still open, but I claim that it is not hopeless. And this is a very good combination when you have, this is a very good situation when you have an interesting long-standing problem which is open but not hopeless. Now, why? Let me explain a little bit why I am so optimistic. My optimism is based on the theory of prismatic cohomology. This is a recently developed, this is a cohomology theory for algebraic varieties over p-adic rings, developed a few years ago by Butt and Scholze, and then reformulated in even simpler terms by Butt and Lurie. And it is this theory which allows us now to make some conjectures, and I hope it will also allow them to prove them or maybe to disprove them. Now, let me say a few words about my recent work. In a recent e-print, I formulated two conjectures about the problem in question, and I hope that the conjectures are true, and I hope that they are provable. This doesn't mean that I can prove them, but I hope that somebody will prove them or maybe disprove them in a relatively near future. Let me now briefly describe the conjectures. Let G be a reductive group. First of all, I want to give a kind of preliminary definition or name. Let G be a reductive group, and let P be a parabolic subgroup of G. I will say that P is Shimurian if its unipotent radical is abelian. The name is mine, it's not conventional. And my name is due to the fact that such parabolics are related to Shimura varieties and also to Hermitian symmetric spaces. Let me explain what this condition means if G is the full linear group of order H. In this case, the Shimurian parabolics are the stabilizers of subspaces in the H-dimensional vector space, while arbitrary parabolics are stabilizers of flags. In other words, in general, parabolic in GLH corresponds to a flag, and it is Shimurian if and only if the flag is very short. The flag consists of only a single vector space. Now, another example is if G is an exceptional group of type E7. Then it is known that in such a group, Shimurian parabolics, in this group, there is one and only one conjugacy class of Shimurian parabolics different from the group G itself. So, in some sense, this explains why I put E7 into my table. In the case of E8, it is known that there are no Shimurian parabolics except the group G itself, and this extreme case is not very interesting. Now, let me say something about my recent e-print. In this e-print, I defined certain stacks. More precisely, for any reductive group G over the ring of, let's say for any reductive group G and any Shimurian parabolic P in G and any positive integers M and N. I define certain stacks denoted by BT N M G P. And then I formulate two conjectures. The first conjecture says that these stacks are algebraic. This is proved if both truncation parameters M and N are equal to 1. And the second conjecture is about the relation between the stack BT and MH mentioned at the beginning of my lecture and the new stacks. The second conjecture says that BTNMH is canonically isomorphic to the disjoint union of the stacks BT and MGLH-P, where P runs through the set of conjugacy classes of Shimurian parabolics in the group GLH. Okay, so I said that I defined certain stacks in my ePrint. I cannot give the definition now, but let me say something about the nature of definition. The definition of these stacks is based on the prismatic theory. Basically, the stack in question parameterizes G bundles on a certain we have to define the groupoid of R valued points of our stack, and the procedure is as follows. First, we path from a ring R to a certain stack, which is called the symptomification of R, and it comes from the prismatic theory in the format developed by Barth and Laureates. So the first step is to produce the stack, and then we have to consider G bundles on the stack and maybe to say some extra words. So the definition is not very elementary in general. However, if our truncation parameters M and N are both equal to 1, then this sophisticated definition can be reformulated in essentially elementary and traditional terms. And if you want to learn about the definition in this particular case, you can look at the extended version of this talk, which is available, which is probably posted online by the Shopper Foundation, but independently of this, I posted as an ePrint in the archive, and this is my most recent ePrint. So now we can leave it. So I plan to say something about Shimura varieties, but I understand that it's too much for this talk. If somebody has questions, of course, so we will be able to ask them during the Q&A session. Thank you very much.
Thank you, Professor Drinfeld. May I now invite Professor Shing-Tung Yao on stage to deliver his lecture on the gravity of math.
Well, it's an honor to give this talk. I know Sir Runrun Shaw quite well, and I stay in this college a few times, and so it's a good time to come back again. The title of my talk is Gravity of Math. Actually, this is the title of a new book I'm writing, and it's being finished and will publish in a few months. It's about general relativity. I use this title because whoever in the foundation do not like my original title, which says The Journey Through Mathematics. But anyway, I talk about how I did my work in mathematics in the last 50 years. Some of them was never reported in anywhere, so it's kind of something I like to talk about. First of all, I started my research in mathematics in the Christmas of 1969 in the library of Campbell Hall in Berkeley. You can see this hall. This was a building built before Evans Hall was established. This is the same time in the Christmas I met my wife. So at the same time, I got to have the chance to read this paper of John Milner, who actually was my colleague many years later, about 10 years later. So it's interesting. He was a big, famous name already at that time. From this paper, I kind of found exciting because it's a paper about the interplay between the curvature of a manifold and the fundamental group. Each manifold has some topology called fundamental group, which I would not explain. I was very much fascinated by the relationship between topology of a space and its curvature at that time. I was learning about it. So when I read this paper, which was clearly written, I felt very good about it. Well, topology is a very basic structure of the manifold, which superficially has nothing to do with the metric defined on it. Yet the theorems in geometry says otherwise. We are trying to relate topology with the metric defined on it in many important occasions. So when I was writing this paper up, I went to the Xerox room, copying this paper, and I met this guy, Arthur Fisher. Arthur Fisher was a lecturer in Berkeley. He is a hippie at that time. This looks a very nice picture of him. At that point, he has long hair and funny looking. Anyway, I refused to let him to read my paper. He basically kicked me out and read the paper. He was very happy and commented that anything relating geometry with topology should be important for physics. I was not so much into physics at that point, but he made this comment. He was a student of John Wheeler. So although I was not terribly happy with his way to kick me out and read my paper, and this statement he made stay in my mind for a long time. So geometry, topology, and physics have to be treated as a unified subject as far as I'm concerned. This has been going on for the last 50 years for me. But I take geometry as a center instead of physics or topology. Many different people may take different center. So geometry will be the driving force. Well, maybe you can say this partially because at that time I know nothing about physics and I know little about topology. I just started to learn topology at that time. So in any case, that was my initial starting point for doing research. Well, but geometry is really a beautiful subject that cannot resist the temptation to keep on looking into its inner structure. There are many beautiful geometric phenomena to be studied. I consider the key to understand geometry is to understand the concept of curvature. And it is a key. Up to now, I still feel the same thing. It happens that the important bridge between geometry and physics is the theory of general relativity, which concept of where the concept of rigid curvature is seen to be equivalent to the distribution of matter in the space-time that we live. So this is a very fundamental fact that I learned already when I was a graduate student, and I just barely understand a little bit about general relativity at that time. As a result, a large number of my works are related to rigid curvature, and also scalar curvature, which is a trace of the rigid curvature. So when I got interested in the structure of the geometry of space-time related to topology and physics, which I mentioned earlier in Berkeley, one day I suddenly realized that the most fair way to understand the geometric structure is to understand how to construct the geometric structure from scratch. And this is a point of view that I think is very important to me, because in those days, geometers just try to derive some consequence out of something. But I believe that an important thing to do is to actually know how to construct the geometric structure. So, to give you an example, to suppose you want to appreciate this building, for example, this tower in Berkeley. Well, in order to understand the tower, the important thing is to understand how to build it from bricks and stones. And that's what I intend to do. So starting in terms of geometry, what it says is that starting from a topological space, we construct a metric structure, just like construct a building. Over the topological space, we satisfy certain conditions on its structure, on its curvature. So if I want to build a tower, satisfy some condition on its curvature, namely I want to build it tall, and I want to make it to be rather beautiful in some way, curvature will dictate this building. And I want to construct it from scratch by bricks and stones and all that. So from this point of view, when I look at Einstein's equation, which is written on the bottom here, the left-hand side is Ricci curvature. I mentioned R is a scalar curvature, is the metric. The right-hand side is the matter density, matter distribution. So I want to understand, based on topology, how do we know we can support a Einstein structure, which means a metric that solves the Einstein equation. So basic question is how to construct a metric structure based on this equation on a topological space. So it's rather interesting on many things based on this philosophy. So to me, therefore, to understand geometry, topology, and theoretical physics, although I said the center to me is geometry, but on the other hand, the basic tools is analysis and partial differential equations. So we can have bricks and stones, but we still need tools. The tools to put them together is analysis and partial differential equation, because only a partial differential equation would help us to prove existence of structure like that. So without deep understanding of analysis, everything would become superficial. That's how I look at this. Well, this point of view was drawn by many of my brilliant friends. Some of them also won the Shaw Prize. And the subject that we developed has been called geometric analysis after many years development by all our friends together. For me, the first task was to understand functions defined on a manifold, on a space. Why functions? Because functions give you a very good description of a space-time. The class of functions that are defined by the geometry of manifold will determine the geometric structure itself. That's the basic point of view. And this point of view, of course, was already started by many years ago by many distinguished mathematicians. For example, I.M. Gelfond already knows that this is an important way to look at space, but look at the space of functions over the manifold. Sometimes there may not be enough functions defined on the manifold because the topology make it to be difficult to do so. We shall, in that case, look for tris functions. Functions not exactly well defined, but tris in some way. And sometimes in algebraic geometry, we call it sections of line bundles. So they are generalized definitions of functions. Well, there are many important classes of functions that are important. One class is called harmonic functions. Harmonic function was developed way back by Euler, by Lagrange, by Laplace, and all these people. They have already found its importance in classical mechanics, and we have been very much used to it. And also the eigenfunctions defined by the Laplacian, which of course is well known in classical physics. When we do wave, vibration, and all that, we know eigenvalues will play an important role. So these are the same kind of functions that appear in mechanics that we want to use to study geometry. Give you an example. If we are interested in minimal surface in Euclidean space, surface which minimize an area, the coordinate functions that describe minimal surface turns out to be harmonic functions. Well, if we want to study minimal surface in the sphere, S3, the free sphere, the coordinate functions are eigenfunctions. So therefore, it's clear that these functions are closely linked to geometry because these are coordinate functions that clearly describe the geometry behind the space. Actually, my first important contribution was done when I was in, right after I was in Princeton Institute for Advanced Study, was to give a good gradient estimate of harmonic functions defined on a complete manifold where the Ricci curvature is a lower bound. This sounds technical to you, but this is actually the initial first paper I ever did in partial differential equation. This paper made me to know what estimate means. And this paper actually has been more influential than what I thought it would be. So this led to developments of many works that I did with S.Y. Chen, who is here, and also with Peter Lee. The idea behind it led to me and Chen to solve important geometric problems such as Minkowski problem in high dimension, Bernstein problems for maximal space like hypersurface Minkowski spacetime, and the Wilmot-Ampere equation, which is related to a phi sphere. These are important questions in classical geometry. It was supposed to be a well-known problem in those days, and I think I got tenure partially because of some of these solutions in Stanford. Then Peter Lee was kind of just newly come in Berkeley, and he studied with me together to making use of this method to estimate eigenvalues of the Laplacian. And we managed to solve some important questions about how to estimate eigenvalues in terms of Ricci curvature and diameter. And this is very good. And right after we understand this, Peter Lee and I developed methods to understand heat kernel of the manifold. So heat kernel is some kind of function that helps you to understand how heat diffuse on a space-time, on a space. This turns out to be key for many important problems that are related to parabolic equation on the manifold. And this, we developed together an important paper called Hanna inequality for parabolic equations. This sometimes people call it Liao estimate. And this estimate has been fundamental for understanding parabolic equations. And this led to an important development by my friend Richard Hamilton. And at my suggestion, when Richard Hamilton was working on his famous work on Ricci flow, we were in San Diego. I talked with Richard. I said it's important to have important estimate for the Ricci flow. What needs it? I told him this work that I did with Peter Lee would be fundamental. And I was just talking, but I do not know what I'm leading to. But Hamilton gave a beautiful generalization to make it to be workable, and to the point that I was shocked when I read his paper. Although I suggest him the way to do it, but actually he did it in such a spectacular way. And this takes a few years to be accomplished. Not that I told him to do so, he finished it after 1 month. It's after 3 years he established this thing. When he came to Harvard and told me that, I was totally surprised. This becomes a fundamental tool for understanding the singularity of the rigid flow. And in writing up, it takes about 2 pages to write up because you write down the answer. But this is a standard thing in partial differential equation. You find the right estimate, to prove it is probably not hard, but to find the right estimate is the key point. And this is very fundamental for the understanding of rigid flow, which most people did not appreciate. And Perelman did appreciate it. He carried this theory much further, and it became the basic tool for the study of the Poincare conjecture in his paper. The second part of my contribution to geometric analysis comes from the study of minimal surface. And I have to say that when the history actually goes together, I learned this part analysis at the same time when I developed the other theory. I learned analysis and partial differential equation concurrently on the subject of harmonic functions and minimal surfaces. And my good friend, Leung, Simon, and Rick Shern, extremely important for this development. We were in Stanford at the same time. As Rick mentioned, it's 50 years exactly that we knew each other. And so it's a great time for me to say it here. And also later, the friends Ken Ruenberg and Bill Mix all two works, Understanding of Minimal Surfaces. This is a beautiful subject that dates back to the first Fields Medal winner, J.C. Douglas. This is around 1930s. And of course, this was first studied by Plateau, and it's called Plateau problem. My teacher, Charles Morley, did extremely fundamental work in 1949. At the time when I met him, I didn't think he's a great man because I know him so well. But after knowing his work, I know how great he is, just like my student. The fundamental work of Douglas, Radeau, and Morley was followed by Sachs, Uhlenberg, and later by some works of Mix, Simon Yao. This on the subject of embedded minimal surface, which I will talk of, will not be able to spend much time on it. The work that I did with Leung Simon and Rick Shern is actually fundamental in most of the development in high-dimensional minimal hypersurface, and Rick and Simon has done much more further after that. Well, the work that I did with Mix actually has been important in topology. We were the first one to develop the idea of using minimal surface to understand topology of manifolds, three-dimensional manifold. And coupled with the work of Bill Thurston, who was my classmate in Berkeley, and also Cameron Gordon, who was in Texas, it resolved the famous Smith conjecture, which says that any finite symmetry of the free sphere must be linear, conjugate to a linear finite group. This was a famous open problem for a long time. Well, Rick and I have made use of existing minimal surface of certain type to solve the positive mass conjecture in general relativity. So this is very interesting because at the beginning we didn't realize that minimal surface was relevant, but then when time evolves, when we study minimal surface on its own right, we found out that it can be used to solve some problem in general relativity. This conjecture says that the isolated physical space-time must be stable in the sense of energy. And so you prove that the total energy of space-time must be positive. And we introduced several concepts during this course of studying minimal surface applying to general relativity. We found out the method of minimal surface in understanding topology of space-time will lead to study of the topology of manifold with positive scalar curvature. This is initial point. When we apply the stability concept, we found out that it influenced the question of positive scalar curvature. And then, after that, we introduced the idea of geometric surgery, which allows one to study the topology of such manifolds. Those manifolds with positive scalar curvature in terms of spin cobordism. We didn't quite say in that way. This last observation was due to Gromov and Lawson, who also developed independently the concept of geometric surgery. And this is actually a fundamental breakthrough, because an important question in geometry is now reduced to a question of topology. And this is the most ideal that we can do. Questions in geometry, which depends on measuring curvature and distance and all that, is now completely reduced to the question of topology, a concept called spin cobordism. The third method that Rick and I did was to understand the formation of black hole through what we call the Young equation, who discovered this equation but did not know how to solve it. We were the first to demonstrate the existence of black hole when the matter density is large enough. This is a folklore statement made by many newspapers before us, but every newspaper assumed that's obvious. Well, they take it for granted because it looks good, and people thought that it was obvious. Actually, almost no astronomer believed black hole exists until 1980s. Before that, well, I was a faculty in Princeton in the Institute for Advanced Study, where there's a large group of astronomers. And when I mentioned about black hole, they laughed. They said, we don't need general relativity. Newtonian mechanics is good enough. It's just BS to talk about black hole. But in any case, the news media like to talk about it because black hole sounds exciting, something exotic, so they talk about it as if it is there already. But the professional astronomer doesn't believe so. Well, on the other hand, the news media neglect the fact that this important notion black hole derived from general relativity must be verified from the first principle of general relativity. And nobody was able to do it, except in an extremely special case, assuming spherical symmetry and assuming the state of matter, etc., some certain type. But here we derive it in a general principle without assuming any state of matter. So this is a rather fascinating statement, which I believe is still very beautiful film that we did together with Ray. I gave a seminar on this work that I did with Ray in IAS, Institute for Advanced Study. Several brilliant postdoc fellows, including Andy Strominger, who came this time, Gary Horowitz, who was my assistant at that time, and Dimitrios Christodoulou were all there. They were postdocs. And Christodoulou was actually a student of John Wheeler, who was the godfather of general relativity, who was in Princeton. And he told me John Wheeler actually asked him to work on the problem of how to demonstrate black holes should exist. But he was based on different mechanism than what we are talking. So after 30 years, Dimitrios actually has shown great interest in this work. After 30 years, he managed to finish a beautiful paper on how gravitational wave collision may create black hole. So this has been interesting to them. But both Rick and I are much more modest. We did not go around to talk about this field as much as we should. But recent discovery of gravitational radiation wave and a black hole shadow led to awarding a Nobel Prize to several people. But now nobody doubts the existence of black hole. Roger Penrose was given the Nobel Prize, I think, 3 years ago, and he was credited. He was an important man, extremely important man, he introduced a fundamental concept of a closed trap surface. This concept was used extensively by everybody working in general relativity relating to black hole. So in fact, in many cases, an extremal closed trap surface is defined to be a black hole. Well, in any case, let me tell you exactly what we did with Rick. So what we proved is that given a space, a domain, what we call it omega, and we define a radius of this domain. So we prove if the matter density on this domain is bigger than this number, 3/2 pi squared divided by radius squared of this domain. So for example, if you fix the radius of this domain to be the radius of the sun, okay, then it says that if matter density is bigger than or equal to this number, where now the radius is equal to the radius of the sun, then the matter density is bigger than some constant, it will collapse, and black hole will form. Well, this estimate is very concrete. It's not existent theorem, it's just a number. And it turns out this matter density is about the density of the neutron star. So what it says that when the matter density is slightly bigger than the density of neutron star, it will collapse to a black hole. So basically it says that after neutron star, there's not much you can look for except a black hole. This is a statement which astronomers do not seem to know, but this follows from our statement. In a general way, not just for spherical symmetric astronomical object, it's a general statement. Well, there are much more things to be improved in this statement, but this original statement, I think, is a beautiful statement. Well, Rick has been, as I mentioned, it's 50 years that we met each other. We have been doing really good works in all these decades. We have trained many students, and now many of them, most of them are students of Rick, has been dominant the subject in classical general relativity. And we are still moving very fast, contributing to many different branches of mathematics. So we so to say, the modern era of geometric analysis. We have a year in Princeton in 1979 to 1980, and many of us come together. This branch of geometric analysis was basically formed around that time, where many important problems were solved. Well, when I still remember when Rick and I wrote up this paper on the positive mass conjecture, it was the summer of 1979 in Palo Alto, and we lived in a grand house, beautiful grand house in Los Altos. The house belonged to a friend of Doris, who's now the wife of Rick. In the daytime, we work hard, and after dinner, we swim in the swimming pool. So that was a really ideal research life. We were young. So work hard for the whole day, and then go to swim and have a nice dinner. Dinner in Moon Palace in Palo Alto. Well, after Rick moved to California, we saw less of each other. At Harvard, I was more influenced by my colleagues in the physics department, where I even becomes one of the faculty of physics department. I spent more time on questions related to string theory and algebraic geometry. So Rick said that I become the algebraics. Not quite. Well, it's fascinating to see how physicists come up with concepts that were alien to mathematicians and vice versa. And this is useful to me, I feel. Well, the physicists like to leap forward simply because they want to reach out their goal fast without caring too much on the background. They don't want to care about proving something rigorously. They come up with beautiful concepts, but they're rarely capable to prove with theorems, to prove what they claim. I'm talking about quantum field theory largely. But mathematician was able sometimes to prove these things after the physicists translate statements into mathematics. And this is really important because this means that the physical intuition coming from these claims by physicists cannot be too far from truth, because they come up with a concept which surprises us, and yet we can prove it. This is especially true for statements coming in string theory. String theory cannot be verified by experiment currently, but they predict deep statements that are not known to mathematicians. And we prove it by rigorous manner, which indirectly shows that the physical intuition behind string theory are basically right. So this becomes some form of experiment. Well, relating string theory, I should come back to the Einstein equation again. Calabi made a conjecture, and I solved it in 1976, and this led to the proof of existence of this equation, which led to demonstrate existence of a space-time which is vacuum. And that means a space-time with no matter. And yet, there's some internal symmetry of this space-time, namely supersymmetry. So this is a very important breakthrough in both algebraic geometry and later for string theory. So when I solve this problem, I use it to solve several important questions, classical questions, appear in algebraic geometry. That make me instantly famous in 1976. And I think I got a Fields Medal based on these applications. And at that point, physicists do not care about Calabi conjecture. But the math community was excited because many important problems appear in algebraic geometry was solved by the Calabi conjecture. This including some famous question about projective plane and some inequality, which is called Miyota-Yau inequality and all that. After doing that, I was very busy refining the conjecture to many important cases, the non-compact and singular manifold. So I worked on this conjecture for 6 years, and it was solved in 1976. After 2 weeks, I got married. So my wife has been always inspiration to me. And in 1979, I met many students of Stephen Hawking, not because of Calabi conjecture, but because of the positive mass conjecture. And I've been good friends with them. And Calabi conjecture is well known. We have found many explicit solutions to the vacuum Einstein equation. And Gibbons and Hawking actually knows this well. They use something called wake rotation to find many such metrics because they know such a metric should exist now. So far, only non-compact version was found. And then I have these young guys, namely Strominger, Gary Horwitz, and they were with me in Princeton. In 1980, I was talking with them. So Gary was my assistant, as I said. He told me this great young man from MIT, Andy Strominger, really know supergravity well. It would be great to learn something about supersymmetry from him. So I invite them for a dinner together and tell them what I feel about geometry. The Calabi conjecture provides very interesting vacuum solution to Einstein equation. And then I said, this should be useful. And then their answer is that this is totally garbage, useless for physics, because we are assuming the structure, the metric to be Riemannian. They call it Euclidean, but not Lorentzian. So they say it's absolutely useless. But then I found that interesting no matter what, and I feel these are beautiful subjects to be constructed. I still push on working on it, and I felt this such a beautiful geometry. How can that be not recognized by Mother Nature? Then in 1984, when I was visiting my family my wife and my 2 children, who is only 1 and 3 years old. And so I went to my wife's office in La Jolla, which is facing the beautiful blue ocean. And suddenly I got a call from my secretary, Miss Underwood, in IAS. And well, I was talking with her. She told me that there's these 2 young fellows were looking everywhere under the sky to me. This is Andy Strominger and Gary Horowitz. So I called Andy. I know him well. He said he was anxious to know whether what I told him in 1981 is true or not. He said, now we have an exciting time. We'd like to know whether such a thing exists or not. And he spelled out the condition that he need for such a space. When I confirmed this exactly what I told him in 1981, he was truly excited that such a space exists, because it is something that you cannot construct by hand. So he was very excited about it, because that's the first revolution of string theory, so to speak. And they need examples. If they don't have example, the whole theory is somewhat vacuum. Then after talking with Gary and also Andy, Ed Witten called me up. I actually knew him because I was in Princeton, and he actually gave a different proof of the positive mass conjecture. And he talked, and then he wanted to know how many such manifolds exist, because he knew that it exists already, because I told them. Then I said there may be 3 of them, because the mathematician did not know that many examples. In most cases, we do not care that much about examples at the beginning. And then the physicists want to know examples. When I told him there are only 3, he got very excited. He said, now that the universe can be computed because there are only 3 examples. So he got so excited, he flew to San Diego to meet me next day. It's extremely efficient. So we talked for the whole day, from morning to night. And then by the time when he arrived, I told him there are many more than 3. And I don't know how many. But in any case, he got so excited, he told me, you guys should work on this, because this is a time, like the good old days when quantum mechanics was discovered. Any people who contribute would be memorized in the history. That's what he told me. I still remember vividly. Well, it didn't work out that way, but still there are many interesting, important developments in string theory that are fundamental to mathematicians and to physicists. They wrote a groundbreaking paper creating this beautiful model, and it was nice for them to call this manifold Calabi-Yau manifold. Well, these are good friends, great that they call me that way. And after a long time, I start to think that Calabi is my first name. It's a statement I make when Calabi has his 70th birthday, and Calabi was very pleased. Well, it's fair to say that without the input of string theories, we would have much less understanding of such important manifolds. The manifold appears as a fundamental tool not only in algebraic geometry, but also in number theory. This is a very important class of manifold in algebraic geometry that has been studied by mathematicians for more than 100 years. One important class of manifold is called K-free surface. K-free surface was studied by several important algebraic geometers. One is called Kunma, one is called Kahler, one is called Kodaira. Kunma was a 19th century mathematician, and they've been studying this class of manifold, the special case called K-free surface, for a long, long time. If you go to any seminar in algebraic geometry, K-free surface would almost for sure mentioned. So Calabi-Yau manifold, including many important class of manifold, some of them are fundamental for algebraic geometry and also fundamental to number theory. So now we have witnessed a beautiful cooperation of mathematicians and physicists. And this is great, I think. It's just like in the good old days when the Greek scientists like Riemann, like Gauss, they work together with mathematicians and physicists. And Now, I remember in this meeting in 1985, in the spring, that was the first revolution in string theory meeting in Argonne Lab. I was asked to give a talk. And I start to mention there are many class examples of manifold of this type. But then there's only only one manifold which has an ordinary number equal to -6. This is an important construction I make during my trip flying from San Diego to Chicago. This is an important manifold. Why? Because this manifold exactly reveals that there are only 3 families of fermions, which was observed in nature. So there are many Calabi-Yau manifolds. There are millions and millions, more than millions, 10 to the power maybe 100 or so. The thing is that most of them do not satisfy what nature wants. Nature wants that there are only 3 families of fermions. And to be ordinary number equal to -6, so far we have only found maybe a few of them. So if nature wants it, they would let us to find it eventually. Not as many as what the physicist says. Anyway, after I finished this working with the physicists, I start to work with Ken Ruenberg based on completely different reasons. I was trying to generalize the concept of Calabi-Yau constructions to the existence of Hermitian-Young-Mills connection on a stable bundle. This actually is a fundamental question in algebraic geometry again. And to me, the difficulty of this proof is just as good as Calabi conjecture. And Ken Ruenberg and I have been working really hard on this problem. And it was finally solved, but really we have day and night not sleeping for quite a few days, quite a long time. And I consider this a very natural construction and should be important for physics also. I told Ed Witten that this should be important for string theory because Young-Mills connection is clearly important, but he told me that the answer is no. But after a year, again, he wrote a paper, and understanding this is important for heterogeneous string theory. So sometimes physicists may not know what they want until when they need it. But it's okay because both the Calabi conjecture and this Hermitian-Young-Mills connections are actually extremely important for the subject of algebraic geometry and Kähler geometry. So this is one of the best work I've done, and this done with Ken Ruenberg. I think because there's discrimination against women, and this paper was not recognized as much as it deserved, although it is recognized, but not as much as it should be. Well, this would be considered as a major tool of how nonlinear analysis is applied to algebraic geometry and in physics. And well, most of this power use PDE, partial differential equation, which is not reachable by algebraic geometry. Algebraic geometry cannot quite reach the very transcendental part of the geometry. And fortunately, analysis could do it. And I think this is a very important statement that algebraic geometry still need to polish their method. There are several important consequences of the Calabi conjecture and the Hermitian-Young-Mills connection that has not been provable by traditional algebraic geometry. And some of these are very important statements, which I do not want to go into. So, in other words, after 40 years, many of the important applications are still the only methods to achieve those fundamental results that I found in algebraic geometry. The reason, I think, is that algebraic methods cannot understand how to handle manifolds with infinite fundamental group. The fundamental group could be truly transcendental, and they don't know how to handle it. Always they need to use the fact that the fundamental group is residually finite, or in some ways algebraic, and they could not go beyond that. So they could not quite prove this statement. Well, then Hitchens introduced this concept, a good friend of mine, of Higgs field. Coupling with Hermitian-Yang-Mills theory, it becomes very effective in studying modular space, and was shown by Carl Simpson in 1995. And this becomes a very important tool called Higgs field, is used in algebraic geometry and in number theory. Some of them got the Fields Medal based on that. The analysis behind Higgs field is truly fundamental, but they are the same argument as the one that I gave with Ken Wunberg. So that's why I said Ken Wunberg deserves much more recognition than what is known. But in any case, this field of Higgs field has become very popular and important in the up to now, after all these years, 30 or 40 years. Once they assume the thing is true, they assume they know everything. But we don't remember that the analysis is still the important part of it. Well, another major impact of string theory is the concept of meter symmetry, where quite a few of my former students are working on it, who gave talks here. So it took me by great surprise. In 1988, my postdoc is Brian Greene, who is very famous nowadays because he writes many popular books. And he was working with Ron Plesser, who was student of Coleman Waffer. He's a PhD student. They come into my office and suggest some important symmetry, which was proposed by Coleman Waffer, a good friend of mine, and several other people. But they make a suggestion, but they didn't know what to do. They based on intuitive concept from string theory. But Brian Greene and Plesser realized the possibility by conceive concrete examples of Calabi-Yau manifold, namely a quintet. This was then followed by very detailed calculation by Philip Candelas and his group. And this becomes a very important revolution in algebraic geometry. It linked Hodge theory, a very fundamental theory in geometry, the period of cycles, and it was able to link them together with something called enumerative geometry. Enumerative geometry is geometry to count things on a space. And a typical example is this statement, which was proposed by Maxime Kontsevich, is that the number of rational curves of degree d in the projective space passed through 3D minus points is given by this formula. It's very explicit. So this is a formula that counts rational curves. And on the other hand, we can relate it to Hodge theory and cycles. This gives you a very beautiful tool to calculate things. And some of this calculation was conceived and hoped to be done 100 years ago. But so far, up to then, nobody was able to find any formula until the string theory proposed a formula based on conformal field theory. And then it's amazing that we actually can prove it. And this is an example of very complicated formula that was not known to mathematicians, was inspired by string theories, and we proved it by completely rigorous method. No intuition from physics are needed. But on the other hand, that's important. The formula was found by physics intuition. That intuition is extremely important for us to prove it. Without the intuition, we could not prove it. So the proof is not follow the intuition, but it inspired the rigorous method. This was very important. This was done by Kevin Liu, my student, my former student, and also brought them together. So in fact, I just make a simple observation. When at that time, a new kind of cohomology was created. So Waffer, Greene, and several other people created. They asked me what is a good name for such a cohomology. I said we need to make it sexy. So we call it quantum cohomology. And to my great amazement, this name sticks on. And it's still, people still call it quantum cohomology. So now, if you pass through the airport and you was questioned what you are doing, you said you are doing quantum cohomology, you may be caught by FBI because you are doing quantum theory, although it's purely mathematics. Anyway, these things has been truly fundamental, and there many people has been working on this subject. So given Tao, Leung, Liu, and myself has proved this rigorously, and that's very important. So there's tremendous confidence in the idea of media symmetry. Many of them are here. And then there was another important second revolution of string theory. I may just finish it now. So this is very inspiring. I should say this is called SYC construction. And I was attending a conference in Trieste in Italy. That was the second revolution of string theory, plane theory come up. Ed Witten was there, and he asked me, he said there's some special class of planes were constructed and by Becker, and Andy Strominger. These are called supersymmetric planes. And he asked me, is this concept natural? And I looked at it, and I studied it for a while, and I said, this is clearly natural. This is a beautiful minimal submanifold, and I think it's great. I didn't realize at that time it was already found by Rees Harvey and Lawson several years before. They call it special Lagrangian cycles. Before that, it was called supersymmetric cycles. But anyway, so now we call it special Lagrangian cycle. They are not defined by holomorphic objects. And I start to think about it carefully and try to understand the moduli space, the space of all special Lagrangian cycles. And I come back and I talk with Alex Sasso, who was my postdoc fellow. We studied the duality based on these planes. And then it comes Andy Strominger, who is being interviewed for a job in Harvard. So we got them together. So we found this work, which is now called SYC, Strominger, Yao, Sasso conjecture. This becomes a very important program for media symmetry. And many people follow, including Conan, who is here, Mark Gross, and Richard Thomas, and they all make important contributions. This whole subject is still being evolved after 30 years, and I think there are many important statements was made and proven to be correct. So I'm found the whole subject is exciting. There are many more things I would like to talk about, but time's up. I think I stop here.
Thank you, Professor Yao. Please take a seat at the center of the stage for the question and answer session. May I also invite Professor Drinfeld on stage and Professor Chen as well for the question and answer session. Thank you.
Hello. Okay, so questions from the audience are welcome. And you can also scan the QR code to upload questions. Maybe I can start the question. So from both Professor Drinfeld and Professor Yao's talk, it looks like there are still close relationship between math and physics. So do you think it's going to be the same in the future? Math and physics interact with each other? Do we benefit from physicists?
If we means mathematicians, then of course the answer is yes. In the past, and Professor Yao interacted with physicists much, and physics and mathematics simply cannot become the same. The nature of the subject, so physics is sort of about nature, and mathematics is in some sense about the logical universe. But the miracle is that the two subjects are closely related, and maybe another related miracle is that the real world is in some sense, can in some sense and to some extent be understood by poor creatures like us. Okay, I have finished.
Well,
Yeah.
I have somewhat different point of view. The question of what nature is different somehow, sounds different. The concept of nature for physicists are much more narrow than what mathematician thinks. Physicists refuse to put in abstract concepts to be part of nature. To us, prime number is nature. To us, a sphere is nature. To us, many important space that we construct, like Calabi-Yau space, are part of nature. We care about the order, the kind of law of nature around them. The law of nature to us is far more important than the objects or what physically call nature there. So as a result, I think mathematicians are proving theorems that are never wrong. That means it will survive in time. But in physics, almost every century, they are updating their truth. There's no real truth, permanent truth in physics. But there's permanent truth in mathematics. That's the major difference. And as a result, I think mathematicians prove many things which are useless, although they are true. And physicists did see something exciting, but they never stood on a very firm ground. So needs mathematicians to clarify it, and finally clarify it good enough so that they can move ahead. Otherwise, after a while, they are stuck. They need mathematicians to help. That's my way of looking at this.
Thank you. So how about the relation between math and technology? Now people were starting to talk about using machine learning to help us prove conjectures.
Well, it's the same. I mean, technology is part of mathematics, really.
Yeah.
The trouble is that they are also trying to leap forward because once it works, they are very happy. They don't want to think about it. AI works in most of the time, and then they are very happy. But they did not want to acknowledge when there are times when it doesn't work. I mean, AlphaGo sometimes can lose one game, maybe lost one game out of 100, but one game is one game. If you come into something, question of life and death, you cannot afford to make mistakes. For example, you use AI to drive an airplane, you do not like to say that 1 out of 10,000 chance it will not crash. So you still have to make sure that it's working. And you need mathematics, rigorous mathematics, to demonstrate what you are using are true, are good. And it's not being done, and it needs to be done.
How about Professor Drinfeld? Can we use machine learning to help us find the questions which are not hopeless?
I know nothing about AI and about machine learning. I was born in, as far as technology in general, well, I was born in 1954, and I was 7 during the first space, when Gagarin first went to space, and so I was raised to believe into the power of benefits of technology, but I have to say that now I'm more and more afraid of the negative aspects we have. So I cannot, here I'm the opposite of being an expert. I'm the just a usual person watching news about the war between in Ukraine, where I was born. Now I'm watching news about the Israel-Hamas war, and in the early days of internet, I remember 1990, people were optimistic about the fact that new technology makes totalitarian regimes impossible. Now we see that this was too much of optimism. Now we see how. So at first we thought that internet gives freedom to humanity. Now we also see how the internet gives a platform for disseminating stupidity, hatred, and so on. So I'm talking not about mathematics, but about what I feel every day, and probably many people in this world people feel every day. So on the one hand, mathematics is good, technology is good in itself, but somehow every positive things, every good things can also be misused, and unfortunately it can be misused many different ways. So we have to be very watchful here. Sorry for my confused speech, but this is what I'm thinking now every day and night.
Okay, yeah. Questions from the audience?
I would like to join the discussion. I'm a chemist, so it's a different discipline. I suppose the chemistry is different from physicists in their collaboration with the mathematicians, because in chemistry we do experiments. Everything has to be proved with experiments. Physicists may not be so easy, for doing the proof as a chemist. But indeed, for chemistry, we do have many help from the mathematicians. We use it as tools. For example, certain transitions in the electronic levels of atoms, etc., they need to satisfy the mathematical equation in order for it to happen. Also, that there are some of the things that we calculate our results, the experimental results. There is, as I agree with you, there's no true results, but it is the reliable results being proven by a calculation of uncertainty. And that means we estimate the variation of the results. In doing the estimation, actually there's a lot of calculus, differential equations. And those things involved. So mathematicians actually the mathematics becomes our tools, rather than the insight that you talk about the physics and the mathematics. So it's a more practical point of view from the chemistry side. That's what I want to say.
Thanks for the sharing. I think
maybe I'll answer a few sentences.
Please, Professor Yang.
Both chemistry and biology has been difficult to organize its fundamental principle. But time has changed. There are much more data that we have collected in biology and in chemistry, and we have much better way to organize data. Of course, AI is one of them, and the last 10 years, development of computer power allow us to organize data much more and better than before. In the last 40 years since I was involved in mathematics, 50 years actually, there has been always a great urge for mathematicians to help to organize biology. So far has not been successful, but I think time has changed. I think in the next 20 years, we will see a radical change in biology and chemistry by using mathematics. And not just in terms of helping you to find things, but organize it in such a form that it becomes a more systematic research that is more fundamental, like physics. And well, we may take 20, 50 years to do, but I think time has changed. We will see much more fundamental understanding of biology and chemistry. And I really encourage universities to invest into such a discipline, a fundamental understanding of biology and chemistry using basic mathematics.
Thank you. So I think there are questions from there.
First of all, thank you so very much for your excellent talks, Professor Yao and Professor Drinfeld. I actually have 2 questions to Professor Drinfeld. You mentioned that in your talk, the stack of BT and H. And we know that a p-divisible group is an inverse limit of finite flat group schemes. And I'm wondering that if this stack makes sense in the level of p-divisible group, and also is this conjecture is well formulated. And the second one, it may not be so relevant to today's talk. That is, there's some special finite flat group schemes. Namely, they're atoll ones. So the equivalent gives the p-adic Galois representations. So I'm wondering if this conjecture gives us more information about those Galois representations. Thank you.
Let me try to answer your first question. So the question, a p-divisible group is essentially a compatible collection of Btn groups for all. Another way to say this is that the stack of p-divisible groups is the projective limit of the stacks Btn mentioned in my talks, the projective limit with respect to n. In my talk, I prefer not to consider, in my talk, I restricted to the case where n is a finite number. Well, in my notation, Btn H is a stack of finite type over Z. Moreover, a deep theorem of Grothendieck said that this stack is smooth. In other words, when n is finite and fixed, then Btnh is more or less an object of classical algebraic geometry. Well, maybe almost classical, so to say. It's not quite classical because it's over the integers rather than over a field, and it's a stack rather than a manifold. But up to this minor details, the object in question looks very classical, and the essential point is that it's finite dimensional. When you pass to the limit when n goes to infinity, then some things become more subtle. For instance, our finite dimensional intuitions can fail us. Then I had several well, and for this reason, and also because of the limitation of time, I preferred not to speak about the new and unexpected phenomena which occurs when you consider the projective limit when n goes to infinity. But of course, this is possible, and this is important. So this was my attempt to answer the first question. Now, as far as I remember, the second question was about the possible applications to Galois representations. Am I right? Can you formulate your second question again?
My second question is that might be not so irrelevant to today's talk. Is that if we consider the atoll group scheme, they're equivalent to the Galois module. So PDV's group is just a p-adic representation, if I'm right. So if this give us interesting information about this Galois representation.
I would say that I hope that, so for me, first of all, I'm not an expert in p-adic geometry. I worked with p-adic things when I was a graduate student, and then quite unexpectedly for me, I was impressed very much by the theory of prismatic homology, and I understood something about it. So I started working in this area. But I'm not really competent. For instance, I have a vague idea of what happened in between the time of my youth and the works by Butt and Scholz on prismatic homology. So for me, the main problem is to understand the stacks B, T, N, M, H. In other words, the reductions modulo B to the N of the stacks of BTN groups. And I would be happy to give, ideally, one would like to have a description which can be explained, let's say, to a first-year graduate student, which can be written, a short answer which can be written on 1 or 2 pages. This ideal hasn't yet been achieved, but I hope that it can be achieved. Now the question is, once we have this description, can one answer some interesting questions about p-adic, about Galois representations and so on. I hope so. Usually when you understand the nature of things, then you get some interesting applications and some answers to questions which were previously asked. Now, an additional, okay, so personally for me, one of the main motivation for my work on BTN groups, so you see, Dieudonné developed what we call now Dieudonné theory of BTN groups, finite groups, commutative group schemes, and so on, at the time when I was a baby. Then my teacher, Professor Manin, wrote his thesis about Dieudonné theory, and now people often call it Dieudonné-Manin theory and so on. As a graduate student, I learned Dieudonné theory by reading Manin's paper on this subject. Now I'm starting to understand little by little the things that I learned as a student. I didn't fully understand it then for various reasons, but now it seems that I'm starting to understand what I, in some sense, learned then. And a related fact is that the theory of prismatic cohomology developed by Bart Scholz and then by Bart Luria. Now, when we have the theory of prismatic cohomology, we see that this theory is not so far from what Grothendieck suggested as a program of what he called crystalline Dieudonné theory. But the problem is that crystalline Dieudonné theory is developed by Grothendieck's student and other people. It's a huge amount of pages, and it's very hard to get through them. But now, when we have the prismatic theory at hand, we have a chance to understand and improve what was conceived by Grothendieck in the early 1970s. So this is the main source of excitement. I hope that when we understand the nature of the stacks of BTNH, and if in some sense when we describe them in explicit terms, I hope that this is not hopeless. I hope that it will have some applications to more concrete number theory.
Thank you, Professor Drinfeld, and also thanks to Professor Yao, Professor Drinfeld's very wonderful sharing. It's a pity that time is up for the Q&A session. So, thank you very much.
Thank you, professors. Please remain on stage for the moment. May I invite Professor Freedom Leung, Head of Shaw College, to present our token of appreciation to speakers and our moderator.